Okay, hello everyone. My name is Triyadi, and I will do presentation of the material mechanical properties and strengthening mechanism. My presentation is from the book source is a metallurgy for the non-metallurgy second edition, edited by Arthur C. Riordan and by ISM. Mechanical properties and strengthening mechanism. The purpose of this chapter is to introduce the concept of mechanical properties and the various underlying metallurgical mechanisms that can be used to alter the strength of materials. Strengthening mechanisms are an important part of material engineering. A metallic material offers a wide range of options in terms of mechanical strength and ductility. Pure metals are typically very soft, but by selecting specific alloying addition and using appropriate heat treatment procedure, they can often be strengthened dramatically. Mechanical properties describe the relationship between the stress acting on a material and the resulting deformation the material undergoes as a result of this applied stress. The concept of stress is in its most general form is a force or load divided by the area over which it acts. For a force F acting over an area, A stress O is main is the strangers is delta. In a conventional engineering tension test, an engineering stress strength curve is constructed from the load elongation measurement on the tensile test specimen. It's a figure picture 3.1. The engineering stress, the stretch used in the stress curve strength curve depicted in the figure picture 3.2 is the average or nominal longitudinal stress in the tensile specimen. It is obtained by dividing the load F by the original area of the cross section of the specimen. You can see the picture of the figure 3.1 and the figure 3.2. This is a strain reduction final and length gauge. And you can see in the figure 3.2 is a strain to fracture uniform strength and the strain more than engineering strength. The type of mechanical properties is the 1 elasticity, 2 plasticity, 3 creep deformation, 4 fatigue, 5 tautness, and 6 hardness. This number 1 elasticity. In the elastic region of the engineering stress strain curve in the figure 3.2, stress is linearly proportional to strain. This region is the straight line that can be seen on the left-hand side of the stress strain diagram, when a crystal is stressed by an external load. The lattice strains in response to the applied stress stroke the relative movement of the atom. When the load is removed, the crystal or object will return to its original size and shape, provided that all the bonds between the atom in the crystalline lattice are not stretched too far. You can see the feature V3.2 this right. And number 2, plasticity. The point at which plastic deformation yielding is observed to begin depends on the sensitivity of the strain measurement. With most materials, there is a gradual transition from elastic to plastic behavior, and the point at which plastic deformation begins is difficult to define with precision. In tests of material under axial loading, three criteria for the initiation of yielding have been used: the elastic limit, the proportional limit, and the yield strength. You can see the picture at the right. And number 3, creep deformation. Creep deformation refers to time-dependent plastic deformation and that occurs when a material is subjected to a constant nominal stress. The rate of creep deformation depends not only on the magnitude of the applied stress, but also on time and temperature. Continuing creep deformation over time ultimately leads to creep rupture, also known as stress rupture. You can see the picture is the strain and first, stage second, and third fracture rupture. And number four is a fatigue, the tendency of a material to break under condition of applied cyclic stresses is called fatigue. Fatigue fractures are different from the ductile fracture that usually result from regular tension and creep loading of most metal. Instead, fatigue fracture is caused by the propagation of cracks that initiated at a single point at few point in the material. And fatigue fractures are almost always brittle fractures. You can see the picture at the right. This is a 1020 steel, and this aluminum 6061 and a point T6. And the magnesium Z31B strip 24. And number five, toughness. Toughness is the ability of a material to absorb an impact or shock load without fracturing. Specimen and notch geometry as well as the manner of load application are all important in toughness determination. For dynamic external rate, loading condition, and when a notch or point or stress concentration is present. Now, toughness is assessed by using an impact test, such as the Karpik impact test, a special measure of toughness called the plane strain fracture toughness (LC) is used in linear elastic fracture mechanics to characterize the resistance of a material to the onset of crack propagation when a pre-existing crack is present in the material. You can see the picture of the metal B is stronger than metal A. This is strain and stress. And six, hardness. Hardness is the resistance of the material to plastic indentation. While the measurement of hardness can involve only a simple stress test or outbound test, it also involves the amount of indentation caused by the application of a hard indenter of some standard shape and material. You can see the picture, it is the same. And this one, strengthening mechanism. Strength of the material can be involved in various ways, as described in the following section. For example, a microstructure with finer grains typically result in both higher strength and superior toughness, compared to the same alloy with physically larger grains. Other strengthening mechanisms are achieved at the expense of low ductility and toughness. Solid solution strengthening. Solid solution strengthening is a mechanism that increases the strength of a metal through the careful addition of specific alloying element, the insertion of substitutional and or interstitial alloying elements produce a strain in the crystalline lattice of the host solvent structure because the solutes of atoms typically have a different size than the host atoms. You can see the atom is small substitutional atoms, interstitial atom, and the large substitutional atom. The effect of grain size. Grain boundaries are effective obstacle to slide because the slip of the discolation in the lattice of individual grains cannot easily cross the high energy barrier of grain boundaries. Instead, dislocation are blocked and pile up at the grain boundaries. Decreasing the grain size also is an effective way to increase ductility. When the grain size is reduced, there are more grains with a greater number or arbitrarily aligned slip planes for the dislocation in the grains. You can see the picture. This is a 0.02% offset steel strength or KSI and the carbon with the long strength. Cold working. Cold working is a process used in metallurgy to shape metal at room temperature or below its recrystallization temperature. Unlike hot working, which involves shaping metals at elevated temperature, cold working is performed at ambient condition. The process typically involves applying force to the metal through process such as rolling, forging, drawing, bending, or extrusion. You can see the picture. This is the grains. And the true and deformed grains, slip plane rotation, deformed grains, broken slip planes aligning with rolling direction. uh, and it's my presentation. Thank you.